In this video, I will show you how to calculate the volume of a solid of revolution using disks and washers. These problems are calculator active, so we will use our graphing calculator as needed. A washer is a disk with a hole in it. For these problems, we will be adding slices shaped like washers to find the volume of a solid. Find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the lines given. For number 12, part A, we will find the region bounded by these three equations, and then we will revolve it about the y-axis. Let's draw a sketch. Y equals 2x squared is a parabola with vertex at the origin. Y equals 0 is just the x-axis, and x equals 2 is a vertical line at 2. So this is the region bounded by the three equations. If we rotate the region around the y-axis, we get this solid that's like a cylinder with a bowl carved out of it. If you take a slice of the solid, it forms a washer, and we can use washers like this one to calculate the volume of the solid. Before we go on, we need to decide if we will ultimately be integrating with respect to x or with respect to y. Notice that if we consider all of the washers, similar to the one I have drawn, they would be stacked vertically. That tells us that we will need to integrate with respect to y. For that reason, we need to rewrite this red function with respect to y. To do that, we solve for x. So we can start with 2x squared equals y. Dividing both sides by 2, we have x squared is equal to 1/2 y. Then taking the square root of both sides, we get x is equal to the square root of 1/2 y. Normally I would say plus or minus, but I'm going to stick to the first quadrant where the initial boundary is. So this is the equation that we will use for the parabola for the rest of this problem. You can picture a washer as a big disk minus a smaller disk. We will call the radius of the big disk capital R, and the radius of the small disk will be lowercase r. Calculating the volume of a solid like this is a three-step process. Step 1 is to find expressions for both radii, the radius of the large disk and the radius of the smaller disk, which is really a hole. Let's start by finding an expression for the large radius, which we will call capital R. It stretches from left to right, so we can find an expression by subtracting the function on the right minus the function on the left. The function on the right is 2, and the function on the left is 0. Obviously, 2 minus 0 is just 2. So this is our expression for the big radius. How about the small radius? To write an expression for the small radius, we will subtract the function on the right minus the function on the left. The function on the right is the parabola, so that is going to be the square root of 1/2 y. The function on the left is 0. So we don't really need to put the minus 0. Step 2 is to find an expression for the area of the washer. The area of the washer will just be the area of the big disk minus the area of the small disk. So the area of the washer will be pi big R squared minus pi small r squared. Well, here's big R and here is small r. So to turn this into an expression for the area, I just need to square this and put a pi in front of it. All right, so now I have pi big R squared, and I'm going to go minus, And I'll do the same thing over here. I'm going to square this and put a pi in front of it. So now we are looking at an expression for the area of the washer. The last step is to find an expression for the volume by integrating the area. When you integrate an area, you add up all of the slices, which forms the volume. So we already have an expression for the area, so all we have to do is integrate. But wait a minute, we need the limits of integration. So I need to know how high these washers are being stacked. I know it's going to go from 0 to something, but I don't know exactly how high. So I can see that the top of this solid is going to be at the intersection between the parabola and the line x equals 2. So I need to set those two equations equal to each other to find the intersection point. Actually, because the vertical line is x equals 2, we're not going to set these equal to each other. We can just plug in the 2 for x. So we end up with y equals 2 times 2 squared, which is 2 times 4, which is 8. That tells us that the y-coordinate of the intersection point is 8. So the washers will be stacked from 0 to 8, and these are the limits of integration. This is a calculator active problem, and I could type this expression into the calculator exactly the way it is. However, it might be easier to type it in if we simplify a little bit. So integrating from 0 to 8, but 2 squared is 4. So I could make this a 4. I see that both terms have a pi in it, so it might be easier if I take the pi and put that out front. So I have the 4, and then I have a square root that's being squared. So the radical and the 2 will cancel each other out, and I will just be left with the 1/2 y and then dy. So this is easier to type in. Type in the pi first. So second pi. To integrate, hit the Math button and choose option 9. We are integrating from 0 to 8. And then we had 4 minus 1/2 y. Well, we have to use x instead of y. And that's it. So 50.265. This is the volume of the solid of revolution. We could have evaluated this integral pretty easily without a calculator, so I think we should do it for practice. The antiderivative of 4 is 4y, and this y will become y squared. Then we divide by the new exponent. 1/2 divided by 2 is 1/4. And I'm going to leave the pi out in the front and apply the limits of integration from 0 to 8. This means we need to find the value at 8 minus the value at 0. I continued to leave the pi out in the front of the parentheses, and here I have the value at 8 minus the value at 0. Because both terms have y in it, we can easily see that the value at 0 is just 0. Applying the exponent, we have this. Performing the multiplication, we have this. So the volume of the solid is 16 pi. So 16 pi is the exact answer, which is approximately equal to 50.265, which we found on the calculator. Part B involves the same region as Part A, except instead of revolving around the y-axis, this time we will revolve around the x-axis. When you revolve the region around the x-axis, it forms a solid that looks a little bit like a cone or a horn that's facing towards the right. Because the region was touching the x-axis, when you rotate, there is no hole in it. So we won't be finding the volume using washers. We're going to end up using discs. To find the volume of the solid, we start with a single slice, a disk like this one. Step 1 is to find an expression for the radius of a single disk. When the radius is vertical, we can find an expression for it by subtracting the top function minus the bottom function. In this case, the top function is the parabola 2x squared, and the bottom function is 0 because that's just the x-axis. We don't need the minus 0, so this is an expression for the radius. Step 2 is to find an expression for the area of a single disk. The area of a disk is always pi times the radius squared. Since this is an expression for the radius, to turn it into an expression for the area, I just need to square it and put a pi out in the front. The third step is to find an expression for the volume by integrating the area. This is an expression for the area, so all I have to do is integrate this. I'm noticing that if I consider all of the disks that make up this solid, the disks are stacked up from left to right. That's why I am integrating with respect to x. The disks are stacked up from 0 to 2, so these are the limits of integration. If we square 2x squared, we get 4x to the 4th power. To find the antiderivative of 4x to the 4th power, I increase the exponent by 1, and then I divide by the new power. 4 divided by 5 is 4/5. Then I'm going to apply the limits of integration from 0 to 2, and don't forget about the pi that is out in the front. This means I need to find the value at 2 minus the value at 0. When I do this, I am going to leave the pi and the 4/5 out in the front. I think I will call this 4 pi over 5, kind of put it all together. But anyway, the value at 2 would be 2 to the 5th power, and then minus the value at 0, which would be 0 to the 5th power. 2 to the 5th power is 32, so I end up with 4 pi over 5 times 32. So the volume of this solid of revolution is 128 pi over 5. Now, these problems are calculator active, so I could have put this expression into the calculator. So that's pi, and then for integration we hit the math button and choose option 9, and we are integrating from 0 to 2. And we are integrating 4x to the 4th power. So that's 80.425 if you round up, or if you truncate, 80.424. Either is acceptable. Part C involves the same region as A and B, but this time we will revolve the region around the line y equals 8. Y equals 8 is the horizontal line at 8. If you revolve the region around the line y equals 8, you get this solid that's like a sideways cylinder with a bowl carved out of the left side. A single slice of this solid is a washer because the empty space represented by this bowl shape leaves a hole in each disk. We can use washers like this one to find the volume of the solid. Step 1 is to find an expression for both radii of the washer, the big radius and the small radius going to just the edge of the hole. Let's start with the big radius. When the radius is vertical, you can find an expression by subtracting the top function minus the bottom function. In this case, the top of the radius is 8, and the bottom of the radius is 0. We don't need the minus 0 part, So an expression for the big radius will just be 8. Now let's find an expression for the small radius. To find an expression, we can subtract the top function minus the bottom function. The top function is just 8, but the bottom function is the parabola, 2x squared. So that's the end of step 1. We have an expression for both the big radius and the small radius. Step 2 is to find an expression for the area of this washer. You can visualize the area of a washer as the area of a big disk minus the area of a small disk. So the area of the washer is pi big R squared minus pi small r squared. So we write pi big R squared minus pi small r squared. This is an expression for the area of the washer. The last step is to find an expression for the volume by integrating the area. Since this is an expression for the area, all I have to do is integrate, and now it's an expression for the volume. When you integrate the area of a washer, you are adding up all of the washers in order to form the volume. Since the washers are stacked up from left to right, from 0 to 2, the limits of integration will be from 0 to 2. I'm noticing that both terms have pi in it, so I like to simplify it a little bit by pulling that pi out in the front of the integral. Obviously, the 8 squared can be written as 64. These problems are calculator active, so let's go ahead and use our graphing calculator to evaluate this. So we have pi, the integral from 0 to 2 of 64 minus, it's probably all I can remember. So let's see, pi, and for the integral we will do math 9. We are integrating from 0 to 2. And then we have 64 minus. And I remember that it's something squared, so I'm going to go ahead and start off the parentheses. And then it was 8 minus 2x squared squared. So 8 minus 2x squared. And then let's close the parentheses and squared again. So 187.658 if you round. So that's it. This is the volume of the solid of revolution. But I do want to go ahead and show you how to evaluate this without a calculator, just in case you run into a situation where you're not allowed to use the calculator. Let's start by expanding 8 minus 2x squared squared by multiplying 8 minus 2x squared times 8 minus 2x squared. First, we distribute the 8, and that's going to give us 64 minus 16x squared. Then we distribute the negative 2x squared, which gives us negative 16x squared plus 4x to the 4th power. Combining these two like terms in the middle, we have 64 minus 32x squared plus 4x to the 4th power. Let's take this trinomial and put it back right here. Be careful, this trinomial needs to be in parentheses until after we distribute the negative sign and change this to a positive 32 and a negative 4. So now we have this. Notice that 64 minus 64 is 0, so these are gone. Now we integrate term by term. So x squared becomes x to the 3rd power. Dividing by the new power gives us 32 over 3. X to the 4th power becomes x to the 5th power. Dividing by 5 gives us negative 4/5. We have left the pi out in the front, and we apply the limits of integration from 0 to 2. This means we find the value at 2 minus the value at 0. With pi out in the front of the parentheses, we see the value at 2 minus the value at 0. Because both terms had an x in it, it's easy to see that the value at 0 is just 0. Applying the exponents gives us this. Performing the multiplication gives us this. Making like denominators gives us this. And subtracting those fractions gives us this. So this is the exact value for the volume of the solid. Part D involves the same region as parts A, B, and C, but this time we are revolving the region around the line x equals 2. When you revolve the region around the line x equals 2, you get this solid that's a little bit like an upside down cone. Notice that there is no space in the middle of this solid. So when we take slices, they form discs and not washers. Also, notice that if we consider all of the discs, they are stacked up vertically. So ultimately, we will have to integrate with respect to y in order to find the volume. Therefore, we need to rewrite the first equation in terms of y instead of x. We did this on a previous problem, so I will just show it to you here briefly, but here is the parabola written in terms of y. We can use discs like this one to calculate the area of the volume. The first step is to find an expression for the radius of a disc. When the radius goes from left to right, you can find an expression for the radius by subtracting the right function minus the left function. In this case, the function on the right is just 2, x equals 2. The function on the left is the parabola, which we will write in the form square root of 1/2 y. So this is an expression for the radius. The next step is to find an expression for the area of the disk, which will be pi times the radius squared. Since this is an expression for the radius, I can turn it into an expression for the area by squaring it and putting pi out in the front. Finally, we can find an expression for the volume of the solid by integrating the area. Since this is an expression for the area, all I have to do is integrate. Notice that since the disks are stacked vertically, I need to integrate with respect to y. These disks are stacked from 0 to 8, so those are the limits of integration. These problems are calculator active, so let's use our graphing calculator to evaluate this. On the calculator, we will have to use x's instead of y's. So we have pi and the integral from 0 to 8. So I'm going to type in pi, and for the integral we do math 9, and we are integrating from 0 to 8. We have to square something, so we are going to need an extra set of parentheses on the inside. So we have 2 minus the square root. So I will do 2 minus and the square root of 1/2 y. So 1/2, well, x. Then come out of there and close the parentheses so that we can square it. And then all we need is the dx. Kabam! 16.755. So this is the volume of this solid of revolution.